All right, so let's talk about composite functions. So just wanted to bring in this quick example from physics. Don't worry too much about it. I want you to get the big picture here. So a composite function is just when the output of one function becomes the input of the next function. So lots of different things can depend on lots of other things. So, you know, how much money I make this weekend depends on how much spare time that I have, and it depends on my wage. And then it might be a piecewise function, because if I work overtime, maybe I get a certain benefit. So I could start with how much time do I have available, and then then a certain proportion of that I spend working, and then the last function is how much money do I make based on how many hours do I work. So something like that. The physics example that came to mind is if you have an object that's accelerating at a constant rate, a, and it has a certain mass, then, well, physicists have sort of figured out that there's this concept of energy, and then it's like physical objects interacting with each other. Sort of energy is this thing that they conceptualize as being conserved, and then it's like you can predict what stuff's going to do by sort of tracking how much energy was there, and then all the energy has to turn into some other kind of energy. So kinetic energy is just a rock that's going at a certain speed and has a certain mass. Well, if that rock was accelerating for 10 seconds in a vacuum with no air resistance or whatever, then velocity is acceleration times time, and their formula for energy is 1/2 mass times velocity squared. Well, if we track all the dependencies here, well, energy depends on velocity, and then velocity depends on time. So for this very controlled experiment kind of situation, you know, you drop a rock at Earth's gravity and you have it in this little vacuum tube with no air resistance. Well, technically it takes the form of E as a function of V, but V is not just a variable. You can expand it so that V is a function of time. And then finally, you end up with something like this. So this is not a physics class, so I'm not going to stress over that too much. I want to just jump into the problems where I just hand you two functions that have two different formulas, and then you want to evaluate something like this. So you distribute the squared over a product. So 8 times t squared is just a squared times t squared, and that'll do it. So if E of v is this, well, E of v of t is this other expression. So let's jump right into the examples. I just want you, this diagram is maybe the most important concept here. And as usual, it gets a little bit have to be a little bit careful when it comes to domain and range problems. So sometimes there's a devil in the details with that, but just want to sort of get through some examples here, and then stuff should be kind of all right. Okay, so maybe let's not do one that's too challenging, but we want to do someone that's at least kind of interesting. So kind of intermediate level, maybe problem 27 looks good. This is 2.3, number 27. F of x is 2x plus 1. Yeah, and I'll write down what the actual, what I'm asking you to do with these next. Okay, so, well, So that little circle, that little circle, it's like an operation, but it's not plus and it's not times, it's of. It's like an O for of. That's why it's a little. That's why it has a kind of a circle shape. And f of g is a new function. Is one point of view, and then how the definition of how do you evaluate that, and what is in terms of the two functions f and g. Well, f of g of x means you take f of whatever g of x is. So you have g of x on the inside, and you plug that into f. So it's a lot easier to just do examples than to try to but you on the inside you have g, so you do g is the first thing you do, and then this is, well, here's g of x here in the picture. What do you do next? Well, if I take f of that, we're not taking f of just plain old x. We don't take f until we've taken g of x first. So f of g of x means you take g, the inside, you work from the inside. You start with just the plain old x, and then you work from the inside out. So you start on the inside with just plain old x, and then you apply x, immediately gets g applied to it, which gets you here. And then that output of the function g, you take f. So it's, with functions, you work from the inside out, applying one function at a time until you finally just get an expression with x's in it. So find f of g of f and their domains. So so the inside thing, you don't have to use colors. I'm going to go ahead and use color. You don't have to, but it's just maybe the special emphasis of what's what. Could help somebody, I don't know. But g of x is, well, the inside, we're not just taking f of x anymore. We're taking, instead of x, we're taking f of smiley face, where smiley face is this inside function, the square root of x. So if f of x is 2x plus 1, then f of the square root of x is twice, little helper parentheses. I like, if I'm trying to explain it, I want to be 100% sure that you understand it. I use helper parentheses. It would mathematically, it'd be, the result is exactly the same without, but I like to really emphasize this thing in parentheses is playing the role of the original x in the original expression, but now we're not taking f of x, we're taking f of the square root of x. So I really like that. So it's just that. So so the only possible problem we can run into is the square root of a negative is not allowed. So that means 0 is actually okay. Everything bigger than 0 is okay, but everything to the left of 0 is not okay. So smiley face is closed interval starting at 0 and then open going all the way out to infinity. G of f is going to be a little different. It's always, you just have to start over. It's like you can't just recycle what you already did. You have to sort of start over. And I could just use green again. I don't know. I'll just use blue. Well, it's not. The inside function is different this time. This time the inside function is this blue 2x plus 1. So we've got running out of space. I think I can fit it. I can save one line if I do it this way. So f of x is 2x plus 1. Well, g is a function that, what does it do? G is the function that takes the square root of the input, and the input is sometimes, because the input might appear more than one place in the output for some other functions, it's like nice to, and it might be nice to group it with parentheses, but so this sort of emphasizes that there's the different parts that it's made out of, but then maybe I simplify just a little bit. That double parentheses doesn't really do anything. So it's the square root of that entire expression, 2x plus 1. Square root of negative not allowed. So when does 2x plus 1 equal 0? That happens when x is equal to negative 1/2. Let's take a quick look here. Negative 1/2 is right at the boundary. We have a couple of sample points here. We could plug in x equals 0 or x equals 1. Well, you'll get a smiley face if you plug in a 0 or 1, because the square root of a positive number is real. Square root of exactly negative 1/2 is also a smiley face, because then you're taking the square root of 0, which is just 0, that's a real number. We're happy with that. But square root of negative 1, yeah, plug in a negative 1, you end up getting square root of negative 1, which is not a real number. So for this problem, the domain is, it starts at negative 1/2, goes all the way out to infinity. Yeah, so that's sort of it for how those work. We can do maybe one more. There are a couple ways of thinking about these. The textbook has its own way of thinking about domains of composite functions that's also kind of equally correct. But for the problems that we're going to be looking at, the two different methods to get you the same result. So I just want to warn you, don't oversimplify too quickly. And one example of that is that's kind of similar to the homework is, this number 36 looks pretty reasonable. So same instructions. F of G, we want to find f of G. G of f. Domain and range. All right, so f of x is given to us as 1 over x minus 2. G of x is provided, that's x plus 2 divided by x. Okay, so f of g of x. I'm gonna go a little bit faster this time. I think f of, well, I'll write down this much anyway, but I'm not gonna do the colors, but we're applying f to not just plain old x, we're applying f to this expression x plus 2 over x. So we take 1 divided by not just x minus 2, but here's where x is in the original expression, and we don't have x anymore. We have, oh man, you won't be able to see it unless I make it a little bit larger. Okay. So one way of solving the domain problem is find the domain before you simplify anything. It's kind of like the difference quotient. You can, the difference quotient is always undefined when h is equal to 0. But that h over h generally cancels out, and that's the only domain, the only way that the domain is different from when you simplify it. So before we simplify anything, the original expression is not defined whenever you divide by 0. And well, there are two different places because there's a big fraction and a little fraction to consider here. So the little denominator equals 0 when x equals 0. So x equals 0 is a frowny face that's not, anything that does not belong to the domain, I like to think of that as kind of harmful to us. That's a frowny face. And we've got a big denominator to worry about. The big denominator equals 0 when, well, there's, okay, so we have x plus 2 over x minus 2 is equal to 0. So that means that'll happen when x plus 2 over 2 is equal, or x plus 2 divided by x is equal to 2. I wish I had a larger dry erase board. You multiply both sides by x, and then subtract x from both sides. You'll get -2 is equal to x. So that's not in the domain. That's not in the domain. And those were the only, the numerator doesn't have a little denominator. It's kind of, those are all the denominators in this entire picture. So domain, oh, we have 0 and we have, well, make sure you get them in the right order. You don't want -2 to be out here to the right. It's everything except for those. So we got minus infinity, we got plus infinity. If we were to keep going forever, we have to avoid these two places. And then, so interval notation says, okay, you know, all these numbers are totally fine, but -2 is the first one. That's a problem. Can't, because we have to divide by 0 if we do that. And let's see, 0 is also a problem. Oh, I see. I thought something looked weird. Okay, so I accidentally wrote down a minus here. Let's fix that. So okay, let me redraw the whole picture. So the bad numbers were 0, which is the first place that it's bad, and then +2. So I was double checking it in my head really quickly, and this one was causing this. Okay, so that one was the issue. Okay, so if I wanted to simplify this, I multiply the big numerator by x and the big denominator by x, and I get x divided by x times x plus 2 over x. So I distribute here. So it's like x times the first term, and then I plus a -2 times x. So the second term is -2, x times -2, x times x plus 2 over x. Well, if x is not equal to 0, then this simplifies properly, and we get it simplifies down to this as long as x is not equal to 0. So that's the f of g problem. So you can pause that for a minute if you want to look at it some more. But it's going to be, yeah, I'm going to want to erase this to just, I want to keep all this information and do it on the same board, so let's do that. All right, so again, for the domain, just if you're going to simplify the function, or if you're asked to simplify it, computing the domain immediately before this step where you simplify is how you make sure you're completely on the right track. Because the actual literal definition is before you cancel out zeros over 0 problems like that, before you cancel out something that could have been a 0 over 0, we'll just take literally what you began with, and then you actually get the actual domain of the function as it was originally given to you. Every time you cancel something, you're making an assumption. You're assuming that those things that you canceled were not 0 over 0, which there are certain places where that's something to watch out for. So g of f, let's do it. The inside function is this. So this could get pretty weird, right? We apply g to, well, we're not taking g of x anymore. G of, if I just wrote down x here and here, then that's g of x. But we're not taking g of x, we're taking g of, so having these big conspicuous parentheses is kind of like using another color. It really makes it stand out. And sometimes it's really important. Sometimes if there's like a minus sign that you have to distribute, actually writing down the parentheses every time is how you make sure you never get it wrong. And sure, sometimes it doesn't make a difference, but it never hurts to include the parentheses around the inside function. So whatever your inside function is, grouping it with parentheses, and then if it doesn't matter, you can remove them as a later step. But yeah, that's what we got. That's what we got here. All right, so what have we got? We've got two little denominators, but they're both identical. So x equals 2 is bad for this problem. So that'll give us a little denominator that is equal to 0. So is the big denominator ever going to be equal to 0? That's this entire of the larger fraction. Well, 1 divided by x minus 2 would have to be equal to 0. You multiply both sides by x minus 2. Well, it looks like this. X minus 2 times 1 over x minus 2. 0 times x minus 2 is just 0. So 0 is equal to 1. Okay, so there are no cases. There's no value of x that can make 1 over x minus 2 equal to 0. So you still need to check 1 over x minus 2 is never 0, so that doesn't contribute any domain problems whatsoever. The only domain problem is at x equals 2. So the domain looks like this. If we want to simplify, then the follow-up step is we multiply by, here's the original, like literally the most immediate output when you apply the composite g of f of x is this thing right here. But the simplification step is we multiply by 1 in the form of x minus 2 divided by x minus 2. Let's get rid of those double fractions as fast as we can because they cause problems. So we have a thing times 1 over x minus 2 plus, so we distribute. So the same thing times the other term, which is 2. So x minus 2 times 2, and then x minus 2 times 1 over x minus 2. And then we have 1 over, 1 over x minus 2, this fraction times a fraction is just you multiply those two denominators together. That's how you multiply a fraction. You just multiply the numerators and multiply the denominators. Now we have a 2 times x minus 2, which distributes like that. Well, we had to make the assumption that x was not equal to 2, but for literally any other x value in the entire universe, g of f of x just simplifies and that's it. We end up with just twice x plus 3. So if we were to graph this, would actually be kind of interesting. We would have 2x minus 3. If we were to go to x equals 2 and plug that in, well, this expression wants to give us 1 as the output, but technically that was not in the domain of the composite function. That was how this function is literally defined as a composite function. And that composite function has us dividing by 0 in 2 different places. Everywhere else, though, it simplifies. So that's like if you're reading all the fine print and being careful, that's this. This is y equals g of f of x. And there it is. So that's the one place where it's very tempting to mess it up is like, it's very tempting to just plug in the home, but if you're being meticulous and if you're being really careful about the rules, you'll see g of f of x is literally this, which has a hole in the graph right there. and that's how you see it. But that's it. That should keep you going.